In fact, let's go ahead and solve this with OD45. And I'm going to show you a little bit of how to construct this. So we're going to not actually build it on the computer. We'll just build it here right up on the board. We'll do board code. Okay? So let's start off this problem with let's build A. Let's build that matrix. That's the most important thing to start off with. So first of all, you would just say something like this. Let's make a vector of ones, zeros, n by 1. Because what I'm going to show you is how to build this with a sparse matrix. Okay? All right? So first of all, I make a row of ones. And then I'm going to say, well, the matrix A is basically it's a sparse diagonal matrix. And what's in it? Well, E1 minus 2 E1, E1. So I'm going to put down there a column of ones, negative 2 and 1. Yes? Oh, I mean ones. I do mean ones. Thank you. Was that? Or else it's a really sparse. Exactly. Okay. Taylor, you good? Yes. Go ahead.
So then the middle one is negative 2 plus 1?
So this will be the middle. Just a bunch of negative 2's.
So, oh, that's times. Okay.
Yeah, times.
I saw a plus.
Yeah, times. It's the pin. Sorry. All right. And I'm going to put these at negative 1, 0, 1. And this is an n by n. Okay, so these are the locations of the diagonals. The 0 is the main diagonal. 1 is to the right. Negative 1 is to the left. Boom. I just built that matrix, filled it up, only the things were non-zero, and now I still have those little endpoints to put on. I could put them in here. I could also just say, look, here's something else to notice. 1n is equal to 1. A n 1 is equal to 1. Right? Put in your little ones. You're done. And you could spy that thing, and it would look pretty for you. Like just, oh, look at that, 3 row diagonals. Okay? Everybody go with that? So there's matrix A. You just built it. Now, oftentimes, in your excitement, and it is truly excitement, you will sometimes go like, oh, awesome, I got the matrix A. What goes with this matrix A is a divide by delta x squared. Don't forget that. You don't have to build it in here because it makes it look ugly. Throwing delta x squareds around. Just do that. But remember, at the end of the day, you have a delta x squared in there. Okay? Make sure to carry that around. All right. Because delta x is small, 1 over delta x squared is really big. So it's going to make a really big difference for you to have that around. Okay. So there's matrix A. Now let's go ahead and pop this thing into a code. And I'm going to show you that, to some extent, it is amazing. This is hopefully why you're in this class, is to learn amazing tricks like this in MATLAB and how MATLAB can change your life. MATLAB can change your life. If it already has, yes, thank you. I'd love to hear it. It's already changed mine too. All right. What can MATLAB do for you? Okay, now here's what MATLAB can do for you. I'm going to solve this thing, and typically what you're going to do is just going to say, look, I want to solve it now using OD45. I'm going to call some right-hand side function. I'm going to give it a t-span. I don't know. I'm going to give it an initial condition. Let's call that u0. I'm going to give it an initial vector for my initial condition. I'm going to tell it, go solve from time 0 to, I don't know, 0 to 10 or something. Whatever you want to do. And then, after that, if you're not going to do anything with setting the tolerances, which generically you probably wouldn't, you do this. But you need to pass some things in for this right-hand side. You need to pass in the matrix A. You need to pass in your dx. Let's start with that. What this is going to do is go call this thing, this right-hand side. Now, what does this right-hand side function look like? So it's a function, and you're computing this right-hand side. What's coming in is your time, your initial condition, your tolerance settings, your a and dx. So you bring all that stuff in. So you've already been playing around with OD45 a bit, yeah? And your right-hand side is as simple as this. 1 over dx squared times a times u. Done. That's it. Right? We said it was 1 over dx squared, a times u. There it is. Pretty amazing, right? Very few lines of code, and you're solving a PDE. Yeah. Dummy is where the tolerance would come in, and if you're not going to do anything with it, just, yeah. You can't not do without it. It'll complain. It'll say, you know, you're not enough inputs, too many inputs. It'll just complain to you until you put something in there to hold it. There you go. That's it. There's your first PDE. How's that feel? Feels good, doesn't it? Yeah. Okay. So this PDE is kind of funny because it's really easy. Heat equation. I could solve it by hand. Okay. A lot of people solve it by hand. So you could say, well, I can make it pretty hard pretty quick. I can say, well, how about we do? I don't know. I'll tell you something to do. How about we do this? U squared uxx plus u to the 4th. I don't know anybody who can solve that by hand. Okay, so it's not that hard to make a PDE a pain for you. Okay. As far as this code goes, you kind of go like, oh, really? All right, well, u dot squared times dot times a times u plus u dot 4. Done. That's power MATLAB. You took something that nobody could solve, trivial modification, you're done. Okay? U squared times uxx plus u4. Dropping the forearms. Okay, you got to start thinking more like that, because I feel passive-aggressive behavior here, and we got to get more like just pure aggressive. Okay? When it comes to coding, you versus the machine, and many of you like have been getting bloodied up and stuff. It's all right. We're practicing so far, but we're gonna, you know, by the end of the quarter, you guys are gonna be mean. It's gonna be awesome. Okay, Taylor, you ready to be mean? Always. Nice. That's what I like to hear. Okay, you guys are gonna have like wrestling names. It's gonna be awesome. Okay, everybody go with that? That's how you do it. That's it. Now, comment. Let's talk about this T-span. You know what we've been doing in class, you can always say, hey, I want to solve this from time, 0 to 10. If you read MATLAB, it'll say, put in your initial and final time. And then what it's going to do is it's going to step forward from 0 to 10 and give you all the points in between, all the delta t's it actually took. Okay, no problem. Usually when you're solving a ODE, that's not a big deal. But now, suppose I actually go solve this thing. Remember, this is now a system of ODEs that can be quite large. I have n of them. So if I chop this up into 512 points, and it takes steps of 10 to minus 3. So if it took steps of 10 to minus 3, there's going to be 1,000 points, 1,000 data points per one step. So there's going to be 10,000 data points with 500, 10,000 slices of time, each one with 500 points. Okay? That's a lot of data. Right? You're getting back like 5 million data points. That's dumb. This is where you're going to run into trouble if you're not careful, because you'll just blow up your machine. Okay? Do stuff like this. Do you really need that much information? No. You might say, you know what? Give me the data every 0.2 steps. It's not so important to do something like this for ODEs that are small. Who cares? You get 1,000 points. But it's 1,000 times whatever n is. Okay? So limit the data that comes out. Once you get above a certain data amount, sometimes, so if you're working like, for instance, on a MATLAB typically will just say, sorry, out of memory. Okay? But it used to be before they did that, it would just start working on your hard drive as for memory. And if you want to spend all day and all year on doing a simple calculation, it's big. This is what you'll just crash your machine.
Wait, are you saying that you enforced T-span having a larger step size, so it's not going to be 45 anymore?
No, well, no, it is still over 45.
Less accurate.
Yeah, no. In fact, what this does, it still takes all the steps at once. It'll still take step sizes of 10 minus 3.
Oh.
It just go along and say, I can throw everything away. Oh, you wanted information at point 2. Okay, I'm going to keep marching along. Oh, you wanted at point 4. I can throw everything else away.
Okay, so that doesn't affect its
Doesn't-
internal
That's right.
tolerance or
It still is always taking step sizes to get that accuracy. Okay, let me try to be explicit. MATLAB doesn't trust you. MATLAB gives you no handle to that delta t. Okay? But it'll let you pick out how much information you want out.